Hello students, welcome to Talk on Civil Engineering. Let us discuss how we will be calculating the stresses in pre-stressed concrete beams. Okay, so here we have an example question. So here is a 300 by 600 rectangular concrete pre-stressed concrete beam is given, and it is pre-stressed by 5 high tension bars of 12 dia. Okay, and it is having a effective stress pre-stress of 800 Newton per mm². Okay, and this tendons is provided at 220 from the bottom of this rectangular section. Okay, and now in this question he is asking to find out what is the moment, the bending moment that can be applied to avoid tension. So that means the tension should be 0. So in order to make the tension 0, how much moment should be applied? Okay, so that is what the question is. Okay, now let us solve this question. So first things, so the area of concrete, so it is 300 into 600, so it will be 180 into 10 to the power of 3 mm². And eccentricity we need to calculate because he has not mentioned the eccentricity directly. So 300 by 600 beam, and he said that the tendon is provided at 220 from the bottom, and the center of this section is 300. So from 300, if you subtract 220, so the eccentricity will be 80. Okay, so E eccentricity is 80 and he has given stress, but he has not mentioned about the, he has not given the pre-stressing force. So we need to calculate the pre-stressing force. So the pre-stress, initial stress in the tendon is 800 Newton per mm². So now let us calculate what is the pre-stressing force, capital P. So pre-stressing force is stress into area of the tendon, the steel. Okay, so it is 800 into, so there are 5 wires are there, 5 bars are there of 12 dia, pi square by 4. So it will be 452.4 kilonewton. Okay, so we got the pre-stressing force, and now we can calculate what is the bending moment. Okay, so firstly let us understand so how we can calculate, how we'll calculate the stresses and how we'll get this moment. Okay, or where we will be using this moment. Okay, so if you see here, if you see from the stress distribution diagram, so this is the rectangular section. So first we'll have the direct stress, so which is positive, that is plus P by area of concrete, and plus we'll have the stress due to the eccentricity of the tendon will have negative on top and positive at the bottom, and this will be plus PE by Z, and then we'll have the stress due to this external load or the moment, so it will be positive on top and negative at the bottom. Okay, so negative in the sense here you will get tension, so this will be compression itself. Okay, so tension will be at the bottom, and we need to avoid this tension. Okay, and at the bottom what will be the stress formula? It is minus, right? Minus moment divided by section modulus. On top it will be plus moment divided by section modulus. Okay, so this equation, so in this equation, so if you add these three, we'll get the resultant, right? This resultant stress will get the resultant stress. This resultant stress should be 0 in order to avoid tension. In order to avoid tension. Okay, so in order to avoid tension, this resultant stress should be 0. So there won't be any stress, 0 stress. Okay, so let us make this equation equated. Let us equate this equation with 0 so that we can calculate what is the moment. Okay, so plus P by area of concrete plus PE by Z minus moment divided by Z equal to 0. Okay, so for that we need Z value, right? So let us calculate what is Z. Z BD square by 6. B is 300. Depth, it is 600 square by 6. So it will be 180 into 10 to the power of 5 mm³. Okay, now let us substitute these values in this equation. So P value, it is 452.4 into 10 to the power of 3 divided by area of concrete. How much we got? 180 into 10 to the power of 3. 180 into 10 to the power of 3 plus P, what is P value is 452.4 into 10 to the power of 3, and eccentricity is 80. E is 80, and Z value it is 180 into 10 to the power of 5. Okay, and moment we need to calculate. So Z 180 into 10 to the power of 5 equal to 0. Okay, so firstly, so let us calculate this equation, the stresses individually. So this will be plus 2.5 and this will be plus 2. Okay, and send this term to that side. Okay. So it will be plus moment divided by 180 into 10 to the power of 5. Okay, so now send 180 into 10 to the power of 5, that is section modulus to this side. So it will be 180 into 10 to the power of 5 into 2.5 plus 2 equal to m. Okay, so it moment equal to 81 into 10 to the power of 6 Newton mm. So that means it is 81 kilonewton meter. Okay, so this is a moment required in order to make the tension at the bottom 0. Okay, or let us check whether this tension at the bottom, the stress at the bottom is tension free or it is 0. Okay, so just add up the stresses at this level. Okay, so we know the direct stress, how much direct stress we got. So it is 2.5. Okay, plus 2.5, and due to eccentricity we got plus 2.5, sorry, plus 2, right? Plus 2 only, right? So plus 2. Now stress due to moment, it is moment divided by 8, right? So moment stress due to moment m, so it is m divided by z, and it is negative because it is below the neutral axis, it is negative. So it is 81 into 10 to the power of 6 divided by 180 into 10 to the power of 5. So it is, how much we'll get? We'll get it is equal to around minus 4.5 Newton per mm square. Okay, so it is minus 4.5. Now the resultant, how much will get resultant? So 2.5 plus 2 minus 4.5. So it is 4.5 minus 4.5, it is 0. Okay, so at the bottom it is 0. Okay, so at the top we'll get some compression stress. So it will be at the top, it will be plus 2.5 and minus 2, because this moment here it will be minus 2, right? Due to the eccentricity, the eccentricity of the tendon, it will be minus 2 on top. Next, plus 4.5. Okay, so it will be around plus 5 Newton per mm square. Okay, so the stress will be something like this, right? So this is how we are going to calculate the moment which is required to make to avoid the tension at the bottom of this beam. Thank you all.